All right, section 5-2 is on linear approximations and differentials. The objective is given the equation of a function f of x, find the linear function that best fits function f at a given point, and use the linear function to approximate f at other points. And we kind of pretty much covered those details actually in the first half of this section. And what we want to do now is go a little bit further into this idea of working with the differentials and using derivatives to actually calculate those differentials. So let's just have a little discussion here about differentials before we go into how to actually calculate these. But the differentials are the dx and the dy. So you've actually seen these for some time now show up when we take a derivative. One way to write a derivative, of course, is y prime. Another way that we said we can write that is dy dx. In fact, to illustrate that, if y is equal to f of x, then we'd say that dy dx is equal to f prime of x. So again, the one way to find the derivative or to write the derivative of y is to write that as dy dx. And you'll notice that your differentials there show up in that notation, the dy over dx. Well, something interesting here happens for us. If we do the following, if we take and multiply both sides of that derivative by dx. So if you take the dy dx equals f prime of x and multiply both sides by dx, notice what happens here. On the left side you have dy dx times dx, and over on the right side you have f prime of x times dx. So on the left side there you can see that the dx's in essence are going to cancel each other out, and we end up with dy is equal to f prime of x dx. So in other words, another way that we can calculate the dy is to find f prime of x and multiply it by dx. And that's what a lot of our problems are going to look like here. We're going to be asked to find dy. And so in other words, given y equals f of x, to find dy, you simply multiply f prime of x. In other words, you find the derivative of f of x, and then you just multiply it by dx. Just put dx right at the end of it. All right, and so like I said, that's what a number of our problems here are going to ask us to do. And so let's look at example 3 here. Example 3 asks us to find dy. It says if y is equal to e to the 3x times the cosine of x. They didn't ask us to find y prime, or they didn't ask us to find dy dx. They said find dy. So again, dy is just equal to f prime of x times dx. So I'm just going to simply find the derivative of this function and then multiply that derivative by dx. So it's a product, so we've got to follow product rule. Derivative of e to the 3x is e raised to some power. It's the derivative of the outside function. Chain rule says you substitute in the inside function, the 3x, and then you multiply that by the derivative of the inside function, which is 3. So there's the derivative of the first function times the second function. And then we add that to the first function, e to the 3x, times the derivative of the second function. Of course, the derivative of cosine is a negative sine of x. So there's the derivative of our function, and we said that to find dy, we take the derivative of our function and we multiply all this by dx. That gives us dy. And to simplify this, I guess, a little bit, or to rewrite this, I should say, a little bit, I'm going to write this as 3 times e to the 3x times cosine of x. And I'll put the negative out front here, so it's a minus, let me put the exponential function first, actually. E to the 3x times the sine of x, and all of that gets multiplied by the dx. So again, to find the differential of y, it's still using the techniques we've learned, actually. It's just finding a derivative, but then at the end, throwing a dx on the end there, multiplying by dx. Let's try another one of those. Let's look at example 4. It says if y is equal to the natural log of the tangent of 5x, they want us to find out what dy is equal to again. Find the differential of y. So again, to find the differential of y, they're not asking for y prime. They're not asking for dy dx. They're asking for just dy. So to find dy, the differential of y, we just simply take the derivative of our function, which is a composite function. So let's follow chain rule here. Derivative of natural log is 1 over something. And chain rule says you substitute in the inside function, tangent of 5x. And then finally, you multiply by the derivative of the inside function. Now, the derivative of tangent of 5x, that's another composite function, so follow chain rule again. Derivative of tangent is secant squared. And chain rule says you substitute in the inside function, which is 5x. And then finally, we multiply by the derivative of that inside function. Derivative of 5x is 5. So there's the derivative of our function. But again, that's not what the question was. It was to find dy, the differential of y. So we take that derivative, and we just multiply it by dx. And again, I would probably rewrite this a little bit here. We really don't need the parentheses there technically. I'm going to put the 5 secant squared of 5x in the numerator over the tangent of 5x in the denominator. In fact, if you wanted to, you could simplify a little bit, I guess, with those trig functions there, but I'm going to leave it like that. And then the dx goes at the end, and I'll just put it at the end there. You could also move it up into the numerator of that fraction too. There's what the differential of y is equal to. It's the derivative of my function times dx. Okay, and again, notice that when you're doing this, the dx just shows up at the end. Okay, to find dy, you just simply find your derivative and then just multiply by dx. Dx just gets added, or not added, really multiplied at the end. All right, let's take a look at one last example. This time, though, they're going to ask us to go the other direction. This time it says, given that dy is equal to this. Dy is equal to 3x plus 7 raised to the 5th power times dx. And they want us to find an equation for y. That is, they want us to find the antiderivative of this. All right. So we just got to think, we got to go backwards here in order to do this. Similar idea, but we're just going to go in the reverse order. Now, first of all, realize that when you're finding dy, the differential y, we just simply multiply the dx on the end. Which means if I'm going to go backwards by in this process, I'm just going to simply divide by that dx to get rid of it. So in other words, when we find dy, the dx just shows up, which means when I start with dy and I want to find y, the dx is just going to disappear for us. So I really just have to focus on my function here is really what I'm going to concentrate on, this 3x plus 7 raised to the 5th power. That's a composite function, so I must have been following chain rule to find the derivative of this thing to get a composite function. So think of the reverse steps here of chain rule. And so we start out with the outside function there. That the outside function is a power function. So chain rule says you take the derivative of the outside function. So I got to think about the antiderivative of it. So since it's a power function, we have to add 1 to our exponent. So we have something raised to the 6th power. And of course, chain rule would say that, power rule would say that you'd multiply by the exponent out front. But of course, since we're finding an antiderivative, I have to divide or multiply by the reciprocal. So it's going to be 1/6 of that. And chain rule says that the inside function stays the same when I take the derivative. So the inside function of my derivative here was 3x plus 7. So I must have started out with 3x plus 7 as my inside function. And then finally, the last step of chain rule says you multiply by the derivative of the inside. But again, since we're going backwards here with finding an antiderivative, instead of multiplying by that derivative, I'm going to divide by it. So the derivative of the inside is 3x plus 7, the derivative of 3x plus 7, my inside function, would be 3. I have to divide by 3, or I'll write that as multiplication by its reciprocal, 1/3. And again, notice the dx doesn't get carried down here because when I take the derivative to find the differential of y, the dx just shows up. I just multiply by it. So in this case, I'm going to divide by it to get rid of it. And then, of course, any time we find an antiderivative, we always have a plus c at the end. So y must equal this. And let's just simplify this here a little bit. 1/6 times 1/3 is 1/18 times 3x plus 7 to the 6th plus c. And the nice thing about finding an antiderivative is you can always check your answer here. And I'm going to go ahead and do that just so you can see our check. Our check is to take this equation that we came up with, y equals 1/18 3x plus 7 to the 6th plus c, and take the derivative of that and see if we end up with what we started with. Actually, we want to find the differential of y, so let's find dy. So we have a constant times our function. The constant stays out front, 1/18. And then your function is a composite function, so follow chain rule. 6 comes out front. Subtract 1 from the exponent, so 6 times the 3x plus 7 is the inside function there, raised to the 5th power. And then multiply by the derivative of the inside. Derivative of 3x plus 7 is 3. And of course, the derivative of our constant, I'll go ahead and put plus 0 here, so we realize we did actually take the derivative of the c, but it's 0. And then we multiply the whole thing by dx. That's how we find the differential of y. And to simplify this just a little bit here, you've got 1/18 times the 6 times the 3, so those guys all cancel each other out. And you're left with just 3x plus 7 to the 5th times dx. So we find out that dy would have to have been equal to 3x plus 7 to the 5th dx. And if you go back, that's what we started with. So in fact, our antiderivative there checks out. All right, and that's the end of this section here for us.